Welcome to presentation 11. Today I will be covering Analog Comparator. As usual, I like to start showing our architecture. The items in greens are the ones that I've already presented. The item in yellow is what we're presenting today, which is the Analog Comparator. The Analog Comparator is part of our Layer 2 presentation. So the agenda for today will be as follows. We're going to do the Analog Comparator background. We're going to discuss Analog Comparator capabilities. We're going to develop our framework. And finally, we'll go through an example program. So let's start with the background information. The Analog Comparator, it allows us to compare two voltage sources connected to the microcontroller. One source is kept fixed as a reference voltage, and this is referred as the negative input. The other source changes based on the external conditions, and that's what we refer as the positive voltage. The output from the Analog Comparator can be used to trigger actions like turning on an LED, stopping a motor when its voltage reaches above a reference voltage. If you need to measure the time between specific analog events, you can enable the ASIC bit to allow the Analog Comparator to trigger an input capture event on timer 1. So in addition to performing its comparator function, it can also trigger a capture of the time when the event happened. Now, this capability is useful in applications where you need to detect voltage levels changes without using a lot of processing power. So what this says is either you're going to set up your comparator or you're going to have your processor spend all its time polling to see if the voltage has changed. Now let's look at the capability. So there are going to be two inputs. One called the AIN0, which is hooked up to port D6, which is pin 12. And then we're going to have the AIN1, which is associated with port D7, pin 13. So the Analog Comparator can directly compare the voltage of AIN0, which is this, to the voltage of the AIN1. Now the AIN1 is going to be our reference voltage. Also, the Analog Comparator can compare the voltage of the AIN0 to an internal voltage, which is 1.1 volts, which is known as the band gap reference. So let me put this in a different way. So you have your reference voltage, AIN1, and then you monitor the behavior of the other source to see how it changes. And then you react according to whether these variable inputs goes above or below your reference. Now, if AIN0 is greater than AIN1, then the output of the comparator goes high. So basically this says if the voltage source is greater than the reference source, then the output from the comparator would be 1. Now opposite, if the reference voltage is greater than the voltage you're monitoring, then the output is going to be low, which is 0. Also, it's kind of good to understand that the AIN0 is called the positive input, and the AIN1 is called the negative input. That's just a convention, not necessarily has to do with positive or negative values. Now, another possibility is the analog comparator can compare the voltage on AIN0 to any of the analog input channels from AD0 to ADC5. So what I mean is the following. So you can set any of these 4 pins, you can configure it, I should say, to use one of those pins as a reference voltage, and you have your variable input here. Now, the analog comparator can compare the voltage on the reference voltage, which is AIN1, to any of the analog channels AD0 through ADC5. So what does this mean? Okay. It means that I can set up my reference voltage here, ANN1, and then I can assign, or I could configure any of these inputs to be the input variable voltage which I'm monitoring. Next, the analog comparator can compare the voltage in any of the DC channels to another ADC channels. Also, the analog comparator can compare the voltage of any of the analog input channels, and that would be AD0 through AD5, to the internal 1.1 band gap reference. So what this means is that I can use any of these pins as the reference or as an input, or I can take any of these pins and compare them to the internal band gap voltage, which is 1.1 as a reference. So that gives you, what I just presented gave you an idea of how you can, different ways you can hook up your voltage sources in reference to the programmer. Now, let's look at the framework. So we're going to do 2 things. One, we're going to review the data sheet as we always do, and then we're going to prepare the include files. The ATMEGA 328P data sheet contains all the information that we're going to need to prepare our framework. Now this data sheet is organized by functionality. Each section has a different function. So let's go to section 27, which contains the analog comparator. And from there, let's go to the register description. Now there are 3 registers in this section. The first one has to do with setting up the comparator to use as input the ADC pins. Now the second registers contains the information relating to all the items that I've discussed priorly. So for example, we have the analog comparator enable, disable. Here we have the analog comparator band gap, which means when we want to use the 1.1 volts as a reference. we have the analog comparator interrupt enabled. Here's where we would set up our interrupts, and then with this bit we would define what's the behavior of how we want the interrupt to behave. And finally, the third register has to do with disabling the digital input. When we use the analog comparator, we should disable the digital inputs to reduce the power consumption. So anyhow, this gives you an idea what's contained on the data sheet as it relates to the analog comparator functionality. Okay, so now let's put together our table for our that we're going to use for our framework. So here, all this information in this table was obtained from the data sheet. So we have 1, 2, and the 3 registers. These are the bits associated with each of the registers and the functions. Now with that information, I created the code, which is a number of defined parameters that we're going to use to access the different bits on the registers. So this is the include file that we obtained. So the framework is implemented as an include file, and the name for this particular include file is framework analog comparator.h. The source code is generated by extracting the contents from the column code, like I said. Then, to prevent any naming conflict with the existing development environment, the parameter names have been modified by adding an X in front. So I have to add this X because the environment already has these names. They've done this work for you. However, here we want to show where things come from. And as a side effect, we have created traceability for our source code back to the ATMEGA 328 datasheet. So when we look at any of our parameters in our source code, we can always trace it through this table back to the datasheet. So let's get going with the sample program. So here we have the 3-volt reference. That's going to be one of the inputs. The AIN1 is going to be a reference which I've set up to be as 3 volts. Then on the variable voltage, which is the one we're monitoring, which is the AIN0, I've hooked up a potentiometer. So as I change this potentiometer, it's going to go between 0 and 5 volts. Next, I have 2 LEDs hooked up to port PV1 and PV0. One LED is green and the LED is red. The idea here is going to be that when I move my potentiometer, and if my potentiometer is above 3 volts, then we're going to have the green light on, meaning we're okay on the voltage. But if our voltage drops below 3 volts, then the red light goes off. So I can move the potentiometer below 3 volts, and then the green light should be off and the red one should come on. So the sample program: at power up, set the initial state as follows. We turn on if the output voltage from port PD6, which is AIN0, that's where we have hooked up our potentiometer, is greater than the voltage at port PD6 IN1, which is our reference voltage, then turn on the LED, the green LED. So basically when you come up, if the input from the potentiometer is greater than 3 volts, you turn on the green light. Otherwise, you turn on the red light. So as soon as you power up, you should know the state of your voltage, whether it's above or below the threshold, by looking at the green and red light and seeing which one is on. Then after the power up, then you're going to be a constant monitor the input voltage. If the input voltage to the port PD6 AN0, which is where we have our potentiometer, is greater than the voltage in port PD6 AIN1, which is our reference voltage, 3 volts, then we turn on the green light. Otherwise, we turn off the red light. So we do the test at startup, and then we constantly are monitoring the input from the potentiometer to decide whether or not we want to turn on the red or green light. Okay, so this is the program, and let's go through this. Let's understand the source code. Let me start by giving you a global view of the program. So we have the init ports, which is going to initialize our ports. We have our init analog comparator, which is going to initialize the comparator. We have two routines related to interrupts to enable and disable global interrupts. Next, we have the initial states, which is going to guarantee that when we power up the program, the LEDs are on the correct state. Then the main program, which is going to make sure that whatever needs to be initialized gets initialized. And finally, we have our interrupt service routine, which is going to do all the calculations and turn on the LEDs in accordance with the inputs from the analog comparator. So let's start with the initial init port. So we have two LEDs, one hooked up to pin B0 and the other one to pin B1. Therefore, they need to be set up to output. Now let's look at the init analog comparator. So this line of code, what it does is disable the input buffer. We do that because we want to reduce the power consumption in the digital input buffer. Next, we have this line of code which enables the comparator. If we're going to use the comparator, the analog comparator, we need to enable it. Next, we disable the band gap reference voltage. That's the internal voltage, because we're going to use the external voltage reference. Next, we enable the interrupts. Now, we have three choices to decide how the interrupt is going to behave. One could be, the interrupt triggers when the rising edge. Another could be that the interrupt triggers with a falling edge, or we could set up the interrupt so it triggers on output toggle. So we've decided that it's going to trigger the interrupt on output toggle. That means that when the voltage goes above or below the reference voltage, an interrupt will be triggered. Now, every time we use a local interrupt for our function, we have to set up our global interrupt, and enable our global interrupt, and that's what this routine is going to do. And then we may need to disable the global interrupt, and that's what this is going to do for us. Now let's go to the initial state. Basically, when we power up the microcontroller, we want the lights to be configured correctly. Either the red light is on or the blue light is on. So if the voltage goes below the reference voltage, then we turn on the red LED, else we turn on the green LED. So let's see how we do this. Okay, if the analog comparator output is equal to 1, that means that the input voltage is greater than the reference voltage. So that's what we ask here. Now, this ACO mask, this is defined on the defined section up here. And basically, it has a 1 in the location of register where the ACO bit goes. So if the ACO bit analog comparator output is 1, then this statement is going to be true. In which case, that means that the voltage is above the reference voltage. I should say the input voltage is above the reference voltage. Therefore, we turn on the green light and we turn off the red light. Else, that means that the analog comparator output is 0, which means that the input voltage is less than the reference voltage. In this case, what we want to do is we want to turn on the red LED and turn off the green LED. So in essence, this routine starts by checking what's the state of the voltage, if it's higher or lower than the reference voltage, and it turns the correct LED, either red or green. Next, we have our main program. So it's going to initialize the ports, initialize the analog comparator, enable the interrupt, and finally it's going to make sure that when we power up, we're in the correct state. Next, it goes to the infinite loop. Now let's look at our interrupt service routine, which is going to trigger on toggle of the input, either the input voltage swing above or below the reference voltage. So the first step here, which is this line, is to disable the interrupt. We don't want an interrupt to trigger while we are in the interrupt service routine. So again, we look at the analog comparator output. If it's a 1, that means that the input voltage is greater than the reference voltage, so we can turn on the green LED. So this is where we check, and if this is true, that means that the analog comparator is 1. What we do is we turn on the green LED and we turn off the red. Now, if the interrupt service routine gets triggered and the analog comparator output is 0, means that we go to the else. It also means that the input voltage is less than the reference voltage. So what we do in this case is we turn on the red LED and we turn off the blue LED. Once we're done with the if statements and or else statement, I should say if statement or else statement, then we enable the interrupts and the program goes back to its infinite loop. So anyhow, that completes the explanation of this program. Okay, so we got to the summary sections. So in this presentation, I gave you a analog comparator, gave you some background. I also talked about the capability. I developed the framework, and finally, we had the example program where we try to put in together everything that I've talked about. So anyhow, I hope you enjoyed this presentation, and thank you for taking the time to listen to what I have to say. And again, thank you very much.